Hello, welcome to this video. So in this video I'm doing an overview of quantum field theory for the gifted amateur, and this is part 2 where I'll be looking at the maths that underpin quantum field theory. It is worth saying that because the maths is fairly advanced and there's a lot going on, I will be just skimming the surface. In that I'll be talking about what the maths does, and I wouldn't worry too much if computationally it still seems a bit confusing, because like with all maths, the only way to get good at the maths is practicing the maths, but this will hopefully show you what maths you need to learn quantum field theory. And again, I am following the content from the book Quantum Field Theory for a Gifted Amateur, but giving an overview of the highlights of it. Hello, so we're going to have a look at the first bit of maths, which is contravariant and covariant vectors. Now it's worth saying that these are two different types of vectors in the way that we use them in physics. In mathematics, there's another way to represent covariant vectors where you consider them as functions that act on vectors, contravariant vectors anyway, rather than vectors in and of themselves. Now, I won't be going down this route, but it turns out that the way that they're usually talked about in physics and the way that they're talked about in mathematics are fairly kind of equivalent. So it's just worth pointing out that there is a different distinction out there than the one I'm describing here, even though the underlying maths is very similar. Well, in fact, it's essentially the same. It's just a philosophically different interpretation of the mathematics. So, to begin with, we have vectors in space-time. That is, we have objects with the components in time and in the 3 dimensions of space. And these kind of vectors are naturally contravariant vectors. And the kind of vectors that one is used to dealing with in high school are again naturally contravariant vectors. We can think of them like arrows. So, in the context of quantum field theory, we're dealing with 4 vectors, that is 4-dimensional vectors in space-time, so these are arrows that exist in 4 dimensions, such as for position, which tells you the position of an event in space-time, analogously to how 3-dimensional position tells you where something is in the 3 dimensions of space. But then we have other vectors, which are also 4-dimensional, but are naturally covariant. And with covariant vectors, we write their index, so the Greek letter, below, so the index is a subscript, whereas in contravariant vectors, the index is a superscript, that is, the index is above. Now, an example of a naturally covariant vector is 4-dimensional derivative operator. And this is 4-dimensional because it differentiates contravariant 4 vectors in space-time. And because it's differentiating a 4 vector, this object needs to be a 4-dimensional version of the derivatives one is used to dealing with. So in A level you learn about a 1-dimensional derivative, and later on you might learn in university about a 3-dimensional version of that, which is described as essentially the gradient, or sometimes called the Dell operator. And then in quantum mechanics we have the covariant four-dimensional derivative, which is a four-dimensional derivative as an extension of the three-dimensional derivative. And the fourth dimension is time, so essentially the four-dimensional derivative can be thought of as a derivative with respect to time attached to the usual three-dimensional gradient operator. And then we have to have some way of being able to swap between contravariant and covariant vectors, because in the algebra, which one uses in quantum field theory and in general relativity, there are covariant and contravariant vectors popping up all the time. And the way you do this is you use something called the metric tensor. Now, the metric tensor can transform a covariant vector into a contravariant vector, but it's also the thing that gives meaning to the idea of distance, in that what we mean by distance in a given space or space-time is encoded within the metric. So the metric has two roles. Firstly, to allow us to define distance, and secondly, to allow us to swap between a contravariant vector and a covariant vector. And we've got an example here where we're transforming contravariant four position into covariant four position using the metric tensor. And it's worth saying that the metric tensor, for the case of quantum field theory in flat space-time, is the Minkowski metric. But if you're worrying about quantum field theory in curved space-time, then the metric tensor will be different. And then lastly, because quantum field theory involves special relativity, because it's how special relativity and quantum mechanics unite to describe quantum fields in space-time, we need a way to swap between a non-primed and a primed reference frame, so an S and an S-primed reference frame. And in my last video I described the Lorentz transformations as essentially sets of equations, but you can combine those sets of equations into a matrix. And that's what that strange triangle almost thing is. That's capital lambda, and capital lambda, because it's a matrix, there's two indices instead of just one. Vectors have one indices, but matrices have two. And this matrix is the Lorentz transformation matrix. It's essentially the matrix version of the set of equations describing the Lorentz transformation, which I mentioned in the last video. And we can use this matrix to transform between primed and non-primed reference frames, as shown here. So that's an overview. As I said, what I'm trying to get across is the idea behind the maths, not so much the computation, which is why there are no computational examples here. However, if you would like to look at these in more depth, please do look at the book Quantum Field Theory for the Gifted Ammeter, because it goes into a lot more depth than I am using here. And now that we've mentioned covariant and contravariant vectors, and how to transform between them, as well as how to go from one reference frame to another, the last bit of maths we need to touch on is the Fourier transform. Now, what the Fourier transform does is it switches from kind of how we describe the wave oscillating in space to how we describe the wave oscillating in time. It allows us to go from one to another, and that is very useful in quantum field theory, where we want to look at how our quantum fields are described, say, in four-dimensional space, but then we want to do something to work out how they're described in something else, so maybe in four-dimensional momentum space. So when we're swapping between describing our field in one space to another space, Fourier transforms are incredibly useful. And if we're going from a function which describes a wave such as the one we have on the screen, and we call this function f of x, so it's a function of four position, because remembering our wave represents a quantum field which exists in four-dimensional space-time, so we have the wave as a function of four position. If we want to turn that into some function of a four-dimensional version of the wave number, which is closely related to four-dimensional momentum or four momentum, then we can use this transform here. Now it's worth saying this transform contains the imaginary number I, and what I does is it tells you about the phase of different parts of the wave, so how far along the cycle different parts of the wave are, and that's what the imaginary number bit helps tell you. And then the kind of magnitude of this Fourier transform tells you about the amplitude of the wave in four momentum space. And it's worth saying with the top equation here, for the four-dimensional version of wave number, I've just called that k, and k by definition is equal to the frequency of the wave in time, sometimes called the angular frequency, as the time component, and then the space components are the usual wave vector, which is a three-dimensional version of the wave number, which is related to the wavelength of the wave in position space. And then also in the top equation I've used x, but as a reminder x is for position, which we can write like this. It's worth saying I'm not including factors of c, where c is the speed of light, and I'm not including them because in quantum field theory we use particle physics notation, in which we just define c to equal 1, so all prefactors of c or 1 over c just vanish, because we define c to be 1. So if we were to include c, then our full position would be c times 2, comma, three-dimensional position. But as I say, we're ignoring c because we're using particle physics notation. And if you take account of the definitions of this four-dimensional wave number, if you like, and four-dimensional position, and you insert these definitions into the top equation, you can write the Fourier transform in terms of the components of these four vectors. And this leaves you with this equation here. And it's worth saying there's a minus sign, and that minus sign comes from the metric tensor, which we're assuming to be equivalent to the Minkowski metric because we're dealing with quantum fields in flat space-time, and that introduces a minus sign. And that minus sign and the Minkowski metric in turn is related to the fact that distance is measured differently in space-time than it is in three-dimensional space. In three-dimensional space we use the Pythagorean definition of distance, whereas in Minkowski space we use something called hyperbolic distance instead. And that just is because it's natural to use hyperbolic distance and special relativity, and that kind of distance has a very important physical meaning, very similar to the meaning behind physical distance in 3D space when we're using the Pythagorean theorem. So this has been an overview of the mathematics. As I say, I wouldn't worry if this seems a bit like I'm just skirting the surface, or if some of this doesn't make complete sense if you haven't seen this kind of maths before. But it's just to give you a feel for the kind of maths involved in quantum field theory, such that if you're familiar with this maths, you know you have the mathematical background you need to look at quantum field theory. But if it's unclear, some of this, hopefully this video has given you a good introduction to what the maths is and why we're using the maths that we're using as well. I hope you like this video, and please check out my other videos if kind of physics or any of this sparks your interest.